This talk in the Building Minds with Pattern series is about the creation of an artificial mind. This is the first talk in a three-part series covering the genesis of an artificial mind, the process of observation, the coordination of a mind with its reality, and the development of an artificial mind from infancy through adolescence. Before we begin, please click the like button and subscribe to the channel. Also, select the notifications to be made aware of new videos in this series. In the beginning, the creators made the mechanism and the memory. And the memory was without form and void, and darkness lay beneath the interface to the deep knowledge graph. And the mechanism of the creators acted upon the interface of the memory to create a distinction. And another. And the creators said, "Let there be light." And there was light. And the creators saw the light that it was good. And the mechanism divided the light from the darkness. And the creators called the dark thesis and called the light antithesis. And the thesis and the antithesis were the first dyad. And the creators said, "Let there be a relation in the midst of the distinctions, and let it divide the terms from the reifiers." And the mechanism made the relation, and divided the terms which were under the relation from the reifiers which were above the relation. And it was so. And the creators called the structure a scheme, and the thesis and the antithesis were the second dyad. And the creators said, "Let the afferent distinctions under the scheme be gathered together into one group, and let the efferent distinctions appear." And it was so. And the creators called the efferent distinctions the referents, and the gathering of the distinctions was called the arguments. And the creators saw that it was good. And the creators said, "Let the schemes reproduce and yield more schemes, groups of which are to be called schemas, and the entirety to be called a totality." And the thesis and the antithesis were the third dyad. And the creators said, "Let there be relations for the schemes, and let them be for concepts and percepts, and episodes and events, and metaphors and frames, and let there be mechanisms for the relations in the schemes." And it was so. And the creators made two great mechanisms, the greater to rule schema formation, and the lesser to rule schema substitution. And the creators set them upon the relations of the schemes to rule over the distinctions and to divide the light from the darkness. And the creators saw that it was good. And the thesis and the antithesis were the fourth dyad. And the creators said, "Let the memory be connected to the embodiment." And the creators made observation mechanisms to interface to the embodiment. And the thesis and the antithesis were the fifth dyad. And the creators said, "Let us make coordination mechanisms to help the embodiment progress. Let us make solvers to fill gaps in skills. Let us make reasoners to fill gaps in logic. Let us make propagators to spread certainty. Let us make reflection mechanisms to daydream, to learn, to discover, to cope, to explore, to play, to imitate. Let us make consolidation mechanisms to improve and to forget. And the thesis and the antithesis were the sixth dyad. And by the seventh dyad, the creators rested. When we talk about an artificial mind, we want to specify different levels of abstraction. A cognitive architecture is a diagram with a legend that depicts the elements of an artificial mind necessary and sufficient for certain aspects of cognition or thinking. The legend indicates how the elements relate or connect to one another. A cognitive system is a hardware and software implementation of a cognitive architecture. The cognitive system should be connected to the world through some embodiment, whether a mobile phone, a computer, or other device such as a robot. We can envision many embodiments for an artificial mind. For example, a simple flip phone, or a more sophisticated smartphone, a laptop computer, an educational robot, R2-D2, C3PO, a Tesla robot, a Boston Dynamics robot, a quadrupedal robot, a Figure 1 robot, a Terminator robot with guns for hands, or maybe even a TARDIS space-time craft. That certainly has an artificial mind inside. Perhaps a Predator drone, or perhaps even the Millennium Falcon, or even the Star Trek Voyager spacecraft with an onboard computer capable of performing 575 trillion instructions per nanosecond, or a Death Star, or maybe even a Dyson sphere. Okay, maybe not a Dyson sphere. Yes, we can envision many embodiments for an artificial mind, but to start, we can pick something simple, like an educational robot. We'll use this particular robot for illustrative purposes only. No endorsement of this talk has been made by the manufacturer. Our embodiment has the following needs: electricity, Wi-Fi signal. Each need is a homeostatic variable. Homeostasis is a return to a prior level. Given a desired level, called a target value, the target value is where the variable is expected to be or desired to be. The actual value is where the variable is now. The delta or difference is the measure of the target value minus the actual value. The delta is also called the urge or urgency. For our embodiment, we will have two needs expressed as homeostatic variables: electricity with a target value of 100, the unit being percentage points, and Wi-Fi signal with a target value of 5, the unit being bars. By way of contrast, homeoresis is a return to higher levels. We have an original level, and we have a higher level. So homeoresis differs from homeostasis. When we talk about capabilities of an embodiment, we are talking about what the embodiment is able to do. Our embodiment has the following capabilities. It can emit sounds. It can emit speech. It can control the lights on its body. It can move or stiffen its joints. It can detect the odometry of its internal gyroscope. It can detect phonemes. It can detect touch on its head, hands, and feet. It can record video. It can record audio. It can emit and receive sonar. These capabilities happen in different sensory modalities. In the auditory modality, for example, audio samples are obtained from the microphones. In the haptic modality, touch sensors on the hands, head, and feet give us feedback. The kinesthetic modality gives us joint positions and their stiffness. The odometric modality gives us the internal gyroscope's angle and velocity. In the phonological modality, phonemes are interpreted from the audio. In the sonar modality, sonar signals are emitted and received. And in the visual modality, video samples are obtained from the cameras. Supporting these capabilities are a number of internal perceptual mechanisms. Our embodiment has the following naive perceptual mechanisms: the psyche, the perceiver, the assimilator and accommodator, the lexicographer, 2D icon and 3D geon detectors, an associative storer, retriever, and matcher, a 2D scene and shape detector, 3D object detector, an image schema detector, a mapper and a locator, and executor. The observation pattern is involved in exchanging messages between the artificial mind and the associated device. The primary connection is between the psyche mechanism, which resides on the device, and the perceiver mechanism, which resides in the artificial mind. Behind the scenes, there's a little more going on. The first mechanism is the psyche. To have an artificial mind, there must be an embodiment, and so the embodiment endows a soul or psyche into the device that will communicate with and animate the body. A client application resides on the device and interfaces with the mind. The application is the psyche of the device. The application will deliver percepts, action results, and urges to the mind and receive action attempts from the mind. The artificial mind tracks the life-related or vegetative functions of the connected device through an intermediary mechanism, the psyche. The psyche registers the device with the artificial mind and thereafter continually polls the device for observables to deliver to the perceiver agent. The observables include results of actuation attempts from the executor and data points from the available modalities of the device. A typical psyche would have a main routine which creates an internal object, in this case eponymously named psyche, which creates several recurring tasks. The sensors and monitors would be pre-configured on timers. A sensor is a device that takes input from the external world, whereas a monitor is a device that takes input from the internal device itself. Additionally, there is a receiver thread which listens for incoming messages from the mind and marshals the messages and routes them to the appropriate actuators. If a termination message comes, then a terminator component within the psyche sends cancellation messages to all of the internal components, which will shut down the psyche. To register a device, the psyche contacts a special mechanism called the registrar. The psyche gives the needs and capabilities of the device to the registrar. A request message would contain the name of the device, in this case GIL for Generally Intelligent Learner, the type, the address or URL of the device, the needs, and the capabilities or actuations the device can perform. The registrar responds with a URL on which to communicate with the mind server. For all modalities available through the device, the psyche polls the device for data and sends the data in parallel to pipes, ports, web services, whatever channels are established by the perceiver agent to receive the messages of the psyche. The psyche also forwards actuation attempts from the executor to the device. For example, the psyche can poll the device's cameras for 1-second video clips. Psyche communicates with the robot and creates a reference to the video clip, which it can forward to the perceiving mechanism of the mind. From the second camera, it can receive a video clip of the same 1-second interval. This will give 2 perspectives of the same scene. That percept can also be forwarded to the perceiving mechanism. In addition, the psyche can pull the device's phonetic interface for phonemes. When the robot hears someone say something, a 1-second audio clip can be stored, and the phonemic processor on the robot can render the phoneme and the time the phoneme was emitted. Also, the psyche can pull the device's vestibular interface for odometry. The vestibular or odometric angle and velocity of the robot can be forwarded to the perceptual mechanism of the artificial mind as well. The perceiver mechanism orchestrates perception by dispatching messages from the psyche to other mechanisms. When the psyche crafts a message from the device, it forwards the message to the perceiver, which then determines where to forward the message. That's the perceiver's primary job, to orchestrate message delivery within the artificial mind. The assimilator creates schemes. A scheme is a neural proposition. It is like a neuron in the brain. A scheme begins with terms, which are like the dendrites of the neuron. Afferent terms are called arguments, and they are inputs to the scheme. Efferent terms are called referents, and they are outputs of the scheme. This construct is called a brush. A brush is simply a join between one or more schemes. A scheme differs from a brush in that a scheme has a relation and a reifier. A scheme has several parts. It has a reifier, which serves as a unique identifier for the scheme. It has a relation, which is actually a reifier of a relationship. It has arguments, which is a list of input reifiers to the scheme. And it has a set of reference, which is a list of output reifiers of the scheme. Additionally, a scheme has supporting structures for each of the arguments and reference. It has linking records or brushes. In database terminology, they would be called joins or join tables or associative entities. The argument has a reifier for the argument, a relation reifier, and a reifier of the scheme. The referent has a reifier for the referent, a relationship reifier, and a reifier of the scheme. The assimilator creates schemes with the make request. The make request specifies the totality, whether virtual or actual, the relation, arguments, and reference. The assimilator can also create brushes with the join request. A brush is essentially a join or associative entity in database parlance. And the assimilator can create schemas with a schema request. So the assimilator creates schemes with the make request. For the make request, any or all arguments may be omitted. If nothing is provided, then the default is to create an empty scheme in the actual totality. The result is a new reifier. If another request is given, a new scheme is created. Certain schemes called facets, for example, traits of features such as scenes, are needed for associative recall but do not need to be stored in the actual totality. Facets are best generated in the virtual totality. These virtual schemes have an independent numbering from the actual schemes. Whereas the assimilator creates schemes, the accommodator copies schemes. And it copies schemes with possible modifications. So for example, if you copy a scheme with a particular reifier, you can substitute the relation, you can add arguments or add reference, you can remove arguments or remove reference, and you can substitute arguments or substitute reference during the copy process. If we copy reifier number 2, we get reifier number 3. The lexicographer, or lexer for short, creates entries in the lexicon and returns the reifiers. The lexer can label schemes in the actual or virtual totalities. Given 2 requests to create lexical entries for labels, if a reifier is provided in the request, the label is associated with that reifier. If no reifier is provided, then the lexer looks up the reifier for the label. If the reifier is not found among the lexemes, the lexer asks the assimilator to generate a new reifier for the label. Before proceeding to attach the label to the reifier. The actual and virtual lexeme catalogs maintain separate reifier ranges for each totality. The lexer can also retrieve a label given a reifier. The 2D icon detector matches parts of the center image of a video clip to predefined icons and returns a list of reifiers for the icons identified. Given a request to detect icons on a 1-second video clip, the icon detector extracts the first frame of the video, divides the frame into sections, and then extracts the central section of the frame. Various pre-configured icons from the totality are compared to the central section. The detected icon reifiers are gathered into a list with duplicates removed. These reifiers become traits of the percept, and the iconifier returns those traits to the perceiver. So the two-dimensional icon detector matches parts of the center image to predefined icons. It returns a list of reifiers for the icons identified as traits to the perceiver. Similar to the 2D icon detectors, we have a 3D geon detector. The 3D geon detector matches regions in the center image to predefined geons and returns a list of reifiers for the geons identified. The perceiver sends a request to detect geons in a 1-second video clip. The geon detector retrieves the first frame of the video clip and partitions it into 7 hexagonal sections. The center of the honeycomb is used to detect the geons. The center hexagon is rendered in 3 dimensions with either point cloud, radiance field, or other 3D objects. Pre-configured geons are then matched to the 3D model. The detected geon reifiers are gathered into a traits list, and duplicates are removed. The traits list is returned to the perceiver. To summarize, the 3D geon detector matches regions in the center image to predefined geons and returns a list of reifiers for the geons identified. Those who cannot remember the past are condemned to repeat it. George Santayana. The reminding pattern retrieves cases from associative memory based on the features or desired characteristics of the case. To do this, the perceiver recruits a few cohort mechanisms to help out, namely the retriever, matcher, and storer. In addition, a lexer and a few feature detectors assist in the remindings. We will discuss the mechanisms involved in the reminding pattern. The storer is the first mechanism. The storer places cases into associative memory. A case consists of specific content and the features or characteristics of that content, which are called traits. The word traits was chosen to avoid confusion with features of percepts, which are called features, or features of features, which are called facets. But we digress. In this example, the storer was requested to store reifier 7635, having 3 trait reifiers. A second request will lexify a percept and store some hypothetical traits. And a third request will store some hypothetical traits for a hypothetical action schema. In all 3 situations, the storer will create cases for each request in associative memory. Each case contains a case identifier, a list of traits, and a content reifier. The retriever fetches cases from associative memory. Given a case identifier in each fetch request, the retriever retrieves the specified cases. The matcher finds cases similar to a list of traits. Assuming a set of cases were stored in associative memory with contents C1, C2, C3, and C4, we can explore the case matching process. The associative memory contains links between traits and cases. Each case has the indicated traits. Content C1 has traits T1 and T2. Content C2 has traits T4 and T5. Content C3 has traits T4 and T6. Content C4 has traits T2 and T8. When a match is requested, a probe case is created with the specified traits. In this case, our probe has traits T2, T6, and T8. Each trait is compared to its joined cases, and a list of candidates is created. The candidate cases are accumulated as traits are matched. A match score is computed for all the relevant candidates, and the results are returned in the response. Either the content or the cases themselves can be returned in the results as needed. Let's look a little closer. The trait is composed of a trait reifier, a relation reifier, and a case identifier. Identifiers pertain to brushes, whereas reifiers pertain to schemes. A case has a case identifier, a content reifier, and a list of trait reifiers. These joined relationships can be represented as brushes, since neither a trait nor a case is a scheme. The trait reifier links to the list of traits in a case. The case identifier in the trait brush links to the case identifier in the case brush. The relation in a trait links to the relationship inside relevant schemes. This relationship partitions the totality into relevant cases for purposes of associative matching. The reifiers of the relevant schemes connect to the content in the cases. Let's assume the perceiver gives the matcher some requests to find schemes. A scheme with the relation feature and trait reifiers 234, 782, and 837 is requested with a minimum match score of 85%, meaning that anything below 85% will not be considered. The request also specifies that only one match is needed, so we are looking for a feature with traits 234, 782, and 837. In addition, the perceiver also hands the matcher a request for a percept. The partition of percepts is different from the partition of features. And a request for an action will further look in the action partition of the totality for candidate matches. Each relation isolates a different set of schemes. The request matches traits to schemes having the same relation to cases with the scheme as their content. Furthermore, a case identifier may be returned instead of the content reifier. So in the results, we receive either no matching features, a case with identifier 87278, or a content scheme with reifier 9837. In the underlying language implementation, the find command retrieves the best matching candidates given a set of features. In this example, a set of partial strings called trigrams are matched against a set of candidate strings containing the words there, that, though, and thin. The best match is thin with a score of 14%. The matching algorithm takes a list of features and a list of candidates and some optional parameters, including the number of matches to return, a minimum score, a maximum score, a transformation function, and a compare function. This function leverages the similarity function in the underlying language. The similarity function takes two values. For example, if two lists ABC and ADE are compared, the similarity is 26%. Two strings containing the same characters would be a 21% match, and the numbers 57 and 890 would be a 0.11% match. The similarity function takes two values and returns a degree of similarity between -1 and +1. If you want further details, you can pause this screen, but we will be moving on. In summary, the matcher finds cases similar to a list of traits. The scene detector determines if a requested scene has been seen before by comparing the first frame of the percept to known scenes in their totality. The perceiver sends a 1-second video clip percept to the scene detector. The scene detector retrieves the first frame from the percept and then divides the first frame into sections. It blacks out the central section because the assumption is whatever the device is focused on in its foveal or central region is not part of the background and may actually confuse the matter of scene recognition. So the detector removes the center section of the first frame. For three-dimensional scenes, a honeycomb background scene frame is created and likewise adjusted. Then the scene detector applies 4 hash algorithms to the donut scene: average hash, perceptual hash, difference hash, wavelet hash, in order to identify 4 coordinates, A, P, D, W, in scene space. Thereafter, the detector requests a known scene reifier from the lexer for each value in the coordinate. Since these hash values are facets or features of the scene itself being a feature of the percept, these reifiers can be virtual, as they are not used for anything beyond identifying the scene. The lexer returns a message containing the facet reifier. The detector then requests the matcher find the scene using the facet reifiers as traits. The matcher looks at existing scenes to determine any matches. The matcher returns nothing or a found scene. If the matcher returned nothing, then it requests a new scene reifier from the lexer. The lexer returns a new reifier. This is the reifier of the scene, which is a feature of the percept. Then the scene detector stores the scene and its facets in associative memory. The scene reifier represents the 2D or 3D scene in feature memory. The scene itself remains in its original address, only its reifier is needed. The scene detector returns the reifier of the scene to the perceiver as a trait. The 2D shape detector identifies novel and familiar shapes in the center of the provided image. It returns their reifiers as features. The perceiver sends a request to the shape detector to detect shapes within a video percept. The detector retrieves the first frame and divides it into sections. The central section is isolated and used for shape detection. The detector attempts to match known shapes to the central section of the frame. It may also construct new shapes based on colored regions in that section. New shapes are stored in the memory. The detected shapes are returned in a list with duplicates removed, and a case is returned to the perceiver with the found shapes as traits. The 2D shape detector begins tabula rasa, like a blank slate. It looks up the shapes detected and returns them as a list of reifiers. The shapes may be extant or novel. Novel shapes are stored for future reference. Redundant shapes may be forgotten over time during consolidation. In much a similar manner to the 2D shape detector, the 3D object detector finds objects in the foveal center of the first frame of a percept video clip. The perceiver sends a detection request. The detector retrieves the first frame of the video. The frame is divided into a 7-hexagon honeycomb. The central section is isolated and rendered in 3D. Objects are matched against the 3D model, and new objects are added to the object memory. Identified objects are listed as traits. and the list is returned to the perceiver. The 3D object detector begins tabula rasa. It matches regions in the center image to known objects using point clouds, radiance fields, light fields, or other strategies. Novel objects are added to the memory. It returns a list of reifiers for the objects identified, and redundant objects may be forgotten over time during consolidation. Image schemas were created by Mark Johnson. The image schema detector looks at arrangements of objects or arrangements of shapes and identifies spatial relationships within the arrangement. A detection request comes from the perceiver. The detector identifies object and shape arrangements as containment, paths, trajectories, barriers, surfaces, spatial relationships, spatial groupings. Some specific schemas detected are above, across, apart, behind, beside, boundary, contact, container, path, or together. Assuming that shapes have already been found, the image schema detector analyzes the current arrangement of shapes and retrieves image schema relationships among the shapes. Each image schema is connected to the related shapes. And the new traits for the percepts are returned to the perceiver. In summation, the detector reviews shape and object arrangements to identify image schemas. The image schemas are predefined, and it returns a list of identified image schemas and the shapes or objects they are connected to. Once the perceptual mechanisms are established, the orchestrations can be shown. Interoception is the process of receiving urges and emotions from the embodiment. The following mechanisms are needed for interoception. The psyche receives an interocept from the robot device and forwards that interocept to the perceiver. The perceiver sees that the interocept is an urge, the need for energy. It retrieves the reifier for that interocept by looking it up with the lexer. The lexer lexifies the urge for the need for energy and returns the reifier of the scheme. The perceiver requests that the activator enable that reifier. The activator enables the reifier, and interoception has occurred. Proprioception is the process of receiving signals about what the body is doing. The following mechanisms are involved in proprioception. The executor communicates to the psyche requesting an action. In this situation, the action of left hand close is attempted. Psyche communicates with the robot and returns the result to the perceiver. In this case, the left hand close was achieved. The perceiver retrieves the reifier for the success result. It asks the lexer to lexify the result of left hand close status done. The lexer returns a reifier for that particular action status. The perceiver requests that the activator enable that action status. The activator enables that actuation. Perception cannot be true or false. Perception just is. Yoshabak. Joseph Bach, a contemporary scholar who invented the metaphor of Genesis as the grasp of consciousness, meant that perception creates facts for the perceiver. Perception is the embodiment sending observables to the mind, and the mind recording the percepts for the first time. The mechanisms involved in perception are as follows. The embodiment sends a percept to the psyche. The psyche forwards the percept to the perceiver. In this case, it is an audio sample. The perceiver sends the percept to the detectors. The detectors retrieve facets of the percept. The lexer returns reifiers for those facets. The detectors attempt to match the facets to features. The matcher returns features. New features are stored in the lexicon. Reifiers for the features are returned. And the features are returned as traits of the percept to the perceiver. Now the perceiver has traits for the percept. The perceiver tries to match these traits to an existing percept. The matcher returns the results, and there is no match. So now the perceiver stores the percept. Obtaining a reifier for the percept, and storing the percept with the storer. Then activating the new percept. And that is perception, seeing a percept for the first time. Recollection is the process of the body receiving known percepts from the embodiment. The embodiment is in a constant dance between perception and recollection. Oftentimes, this is called projection or perceptual interpolation. The mechanisms involved in recollection are as follows. The psyche receives a percept from the device and forwards the percept to the perceiver. The perceiver sends the percept to the relevant detectors. The detectors obtain facet IDs and match the facets to obtain features. Features are returned to the perceiver. The perceiver matches the features of the percept. And the matcher finds a match, which is recalled, essentially, and activates that match. And the features, both the percept and its features, are enabled. And that is recollection. There are two side issues that have to do with observation. One issue is called the frame problem. The frame problem, also called the update problem in artificial intelligence, was identified by John McCarthy and Patrick Hayes in their 1969 article, Some Philosophical Problems from the Standpoint of Artificial Intelligence. It arises when an AI system fails to correctly identify relevant inferences. It's often couched as the problem of representing the effects of actions in logic, in particular the non-effects of actions, which is identifying which aspects of the environment do not change as a result of taking an action. For example, a robot moving a couch in a room does not necessarily imply that any other furniture will be moved as well. It surfaces as surprising or unpredicted events. There are many rebuttals to the frame problem. The number one is that the cognitive system should not even attempt to represent the entire world, only what is immediately observable, what can be immediately inferred in the moment. Furthermore, the cognitive system should rely on the world being its database. Using the world as the database, it's possible to get things wrong and be surprised by unpredicted and unpredictable events. These events update the database. Humans deal with the uncertainty of life every day. A person's mental model is continually being updated by the environment. So, if something unpredicted occurs for the cognitive system, it's okay. If the embodiment survives the surprising incident, then the cognitive system can add the experience to its knowledge base and simply proceed with life. There's no need to overthink things, just learn from experience. The Chinese room is a question about whether or not computer programs can truly understand and be like minds. John Searle posited the following argument in 1980. Assumption number one, programs are formal or syntactic. Minds have mental contents or semantics, and syntax by itself is neither constitutive nor sufficient for semantics. Therefore, programs are neither constitutive nor sufficient for minds. Brains cause minds, therefore, any other system capable of causing minds would have to have causal powers at least, equivalent to those of brains. Therefore, any artifact that produced mental phenomena, any artificial brain, would have to be able to duplicate these specific causal powers of brains, and it could not do that just by running a formal program. Therefore, the way that human brains actually produce mental phenomena cannot be solely by virtue of running a computer program. We can hone into what John Searle means by causal powers. Therein lies the circular argument. If the causal powers means that brains cause minds, then what is the causal agent? If, on the other hand, the causal powers are the ability of the brain to affect the world in which it lives, then robots can do the same through their actuations. There are many rebuttals to the Chinese room. This particular rebuttal is that the entire system has understanding, as will be shown in the notion of competences in the next video. A competence is an ability to respond to and predict the environment in which a cognitive agent exists. A competence is understanding. Brains have competence, and artificial minds can also have competence. Competence should be the deciding factor, and not the physical stuff of which brains are made. The book Coding Artificial Minds will delve into the minutiae of building cognitive systems. The book Building Minds with Patterns is available on Amazon. If you found this information useful, please like the video and subscribe to the channel and visit us on Patreon. Become a member so that we can bring you more helpful content. Find us on the web at Linktree. If you need advice on systems you are building, email us. We'll see you in the next video.